Hello everyone, my name is Vitalii Babenko and today I'm presenting to you the report named Improved Random Forest Algorithm in the task of liver pathology classification by medical images. The report will be presented as follows. In today's world, the niche of artificial intelligence and neural network enjoys the great popularity. This is driven by increasing demand to analyze and process large datasets, which is impossible to do without machine learning techniques. This is true for medical image data, which is not presented in human-inspired form, so it's difficult to process. Nevertheless, neural networks are not the only panacea for solving such delicate problems. There are also ensemble machine learning techniques that are promising for analysis because their approaches to creating and aggregating ensembles of models can suggest appropriate techniques for interpreting the solutions that emerge. In addition, ensemble learning algorithms are faster and more efficient than neural networks, which is beneficial for clinical specialists while creating medical decision support systems. Thus, it can be said that this study aimed to develop an ensemble learning algorithm that can demonstrate the best results in the task of normal pathology classification based on medical images. Before describing the proposed algorithm, a couple of words about the random forest. This is an ensemble algorithm that operates on the principle of bootstrap aggregation, or in short, bagging. By this principle, as can be seen from the figure on the slide, multiple decision trees are trained in parallel on different subsamples of data, randomly generated from a training dataset. Then, the trees are combined by aggregation, in the case of classification by majority voting, to produce the final prediction results. The traditional variant of decision tree training uses a single training data sample on which the best thresholds of informative features are selected, thus forming tree nodes. In our variant, it was decided to use the principle of the group method of data handling, by which tree training performs on two data samples simultaneously. In the first sample, the optimal thresholds of the features are found, and in second sample, the threshold of one of the best feature is selected, which gives the best classification result. Because of this manipulation, we obtain a tree of optimal complexity. Let's move on. The random forest algorithm uses the random subspace method, which means that for each tree, training uses a subsample of features generated randomly from a general set of features. To get rid of randomness, it was decided to use the genetic algorithm, thus finding the optimal subsample of features for each tree, which gives the best classification results, on the third validation sample, which doesn't take part in the training of the tree. In forming an ensemble of trees, it is necessary to aggregate their results to obtain a final verdict. For this purpose, we decided to use the SAATI analytic hierarchy process, which allows us to obtain the weight coefficients of each tree. The weight of a tree depends on its prediction performance on the validation sample. Consequently, it allows us to level out the corruption of the result by the prediction of weak trees. Thus, we propose the improved random forest algorithm that combines the approaches of the group method of data handling, the genetic algorithm, and the analytic hierarchy process. The proposed algorithm has been used to solve the classification problem of the following medical image data. Almost 4 years ago, the Institute of Nuclear Medicine and Diagnostic Radiology provided a database of liver ultrasound images. The images include both normal and pathological cases, like hepatitis, cirrhosis, steatosis, and Wilson's disease. The specialists on the institute have marked the regions of interest on the images, which are highlighted with a red rectangle. We decided to cut these regions out of the images to use them as classification objects. Since the ultrasound images were taken by 3 different sensors, the regions of interest were accordingly divided into 3 general samples, and different classification models were trained on each of them. As can be seen from the table on the right, there is a class imbalance in the reinforced linear sensor data sample, which must be taken into account in the modeling. This slide presents a methodology for solving the problem of liver pathology classification from medical images. If you talk about texture analysis, this is an elegant way to extract informative features from images, since images are two-dimensional arrays of grayscale pixels. Statistical information from them makes it possible to build diagnostic classification models. The results of the modeling are demonstrated in this table, which shows the classification metrics on the objective testing sample. The highest accuracy scores in each of the three samples are highlighted in yellow, so we can say that our proposed algorithm was better than the better-known counterparts. It is also worth noting that all 5 classification algorithms showed a balance in the evaluation of sensitivity and specificity, which was achieved by using a stratification strategy while dividing the samples. The improved random forest algorithm was the foundation for our department's diagnostic decision support system. This system has been implemented at the Institute of Nuclear Medicine and Diagnostic Radiology. Conclusions you can read from the screen. I would also like to thank the Institute of Nuclear Medicine and Diagnostic Radiology for providing data and giving advices to provide this study. Thanks for watching, and glory to Ukraine!